Hello friends, today we are going to design one RE wall and the reinforcement will be geogrid. So geogrid reinforced earth wall. So we are going to take one example and this will be the analysis and design of RE walls. So let's say you have a RE wall, the height of the RE wall design a reinforced earth wall, RE wall, geogrid reinforced. Having height h equal to 9 meter. So very high wall. It is going to be 9 meter height. And the wall fill, RE wall fill, is going to be granular material. Sand and the unit weight of the reinforced zone gamma R is given to you as 22 kilonewton per cubic meter. And the angle of internal friction of the reinforced wall is 40 degree and C equal to 0. And also you know the backfill property. The property of the backfill the property is gamma of backfill, B for backfill, is 18 kilonewton per cubic meter, and the angle of internal friction phi of backfill is 30 degree and cohesion is 0. And the surcharge is acting throughout the reinforced earth wall. So there is a surcharge Q, and the magnitude of the surcharge is quite high. It is 34.43 kilopascal. So this is the surcharge. And the interaction coefficient of geogrid CI is 0.85 and recovery ratio CR is 1. So CR equal to 1. So you need to design. How will you design it? So you know the height of the wall. There is the facial panel. There is the pad. the reinforced zone, and these are the reinforcing element, geogrid, and the height is given to you, h equal to 9 meter. And this side, it is the backfill, and this is the reinforced zone. This is the fill, wall fill. So the total height is given to us as 9 meter, right? How will you design it? So you will have to provide the geogrid. Let's say we are going to provide the first reinforcing element at a depth equal to 1 meter. And the second layer is going to be at z equal to 1.5 meter. So this is going to be 0.5. And the subsequent reinforcing layers are going to be at 0.5 meter. So the vertical spacing between two consecutive reinforcing element SV, here it is going to be 0.5, and the first reinforcing, if you are taking from the center, if I take the center here, this is going to be 0.5, this is going to be 0.25. So for the first layer, the value of vertical spacing is going to be 0.25 plus 0.5, that is 0.75. So we can calculate it. Layer 1. So layer number. Let us see the solution of this problem. And depth z in meter. So this is the direction of z in meter from the top. So you know the value of z, and you can calculate the value of vertical spacing SV in meter. And therefore, you can calculate the tension that is going to develop in the reinforcement. The unit will be kilonewton per meter. So you will be getting TD. Once you get TD, what is the allowable tension? TD multiplied by the factor of safety. So you can find out TA in kilonewton per meter. So you can get TA also. So very simplistic way, you can then calculate for internal stability. The very first, if you want to find out the solution, here you will have to check for internal stability of the wall. And then you will have to check for external stability of the wall. So in internal stability, I have already told you what are the things in internal stability. It is going to be the total length and vertical spacing. These two things you need to calculate. What is the total length of the reinforcing element? From here to here is the total length. And if the failure plane or the slip surface, the failure plane inclined at 45 plus pi by 2, then at any depth, you know, this side, it is going to be length of embedment, and this is called LR. LR is the reinforcement length in non-active zone, and LE is the length of embedment in active zone. This I have already explained in my previous video. So you are well acquainted with the terminology. You are well acquainted with the load transfer, and therefore you can easily calculate the value of LE. So what you can calculate is the length of embedment in meter. So you can calculate it. This will be the calculated value. And then LE provided how much you are going to provide the length. What is the minimum criteria? There is minimum length that should be there. The minimum length to be provided is 1 meter, not less than that. If the LE calculated is going to be more than 1 meter, it's well and good. Otherwise, if it is less than 1 meter, you will have to minimum provide the length as 1 meter and then calculate LR in meter. So LR is to be calculated, and if you add up LE provided and the length of the reinforcing LR, this, if you sum up, you get the total length in meter. So you get the total length of the reinforcement in meter. So friends, very easily we can calculate. With the kind of knowledge which you have, you can do it. There is no problem. So let us see how the things proceed, and keep your calculator ready because it is going to be analysis and design problem. So friends, I will be able to take the layer 1. So if I take the layer 1, first layer, so this is my layer 1. This is the first reinforcement. So this is my layer 1, this is layer 2, this is layer 3, and so on. So first layer, at what depth? Z equal to 1 meter. So what is the vertical spacing? It is going to be half of 1 meter, that is 0.5, and half of the distance between the second layer, that is 0.25. So SV equal to 0.75 meter. Isn't it? So I got this as 0.75. Now the question is, how will you calculate the tension that is going to develop in the reinforcing layer. Now, here you have got the surcharge also, very high surcharge. So, surcharge is acting here on the reinforcing zone. This is the surcharge. It's Q equal to, that's given as 34.43 kilopascal. So that's also given. So friends, let us calculate now what is the horizontal pressure in the reinforcement zone. So PHR will be K in the reinforcement zone. So K in the reinforcement zone, R, this you can calculate, into gamma R into Z plus the surcharge. This is the formula. So this formula is well explained in the previous video and all of you know it. Now how to calculate KR? KR will be 1 minus sine phi r. The value of phi r is already given to me as 40 degree. So let me take my calculator and let us calculate. So 1 minus sine 40 divided by 1 plus sine 40, the 0.217. So this value is 0.217. So here it is going to be 0.217. Gamma R is 22 multiplied by Z, the vertical distance, and the surcharge is 34.43. So you are going to have 0.217 multiplied by 22, 4.774. Z plus 0.217 multiplied by 34.43, that is 7.47. 7.4. So that is the value. You are going to get it. So PHR, you know it. So what is the vertical force multiplied by KR is the horizontal force. H for horizontal in the reinforced zone. And due to surcharge also, it is K times Q. Having got the value of PHR, you can easily calculate the value of tension, design tension or tension developed, which is known to us yesterday. In my previous video, I have already talked about this. This is going to be PHR, the horizontal force multiplied by vertical spacing divided by CR. CR is already given to you as 1. So this is going to be 1. So finally, it is going to be tension developed equal to 4.774 into Z plus 4 times 7.471 into vertical spacing. So already vertical spacing is known to me for layer 1. And the tension that will get developed can be now easily calculated. So PHR Z is already known to be 1 meter. So let's calculate it. So friends, we can calculate it 4.774 multiplied by 1, that is the value of Z, plus 7.47 I will 7.471. Let us take it 1 also. Bracket closed. Multiplied by spacing, vertical spacing, that is 0.75. This gives you TD equal to 9.183. So TD equal to 9.18 kilonewton per meter. That's TD. So having got the value of TD, now go to this layer 2. So layer 2 will be, for layer 2, what will be the value of Z? It will be 1.5 meter. The second layer is 1 plus 0.5. So it is going to be 1.5 meter. So what is the vertical spacing? 0.5 for second layer divided by 2, 0.5 divided by 2. So it becomes 0.5. So the vertical spacing equal to 0.5 meter. So now in this equation, we can easily calculate the value PHR. So here Z is going to be 1.5. So let's take the value of Z equal to 1.5 plus 7.471 multiplied by 0.5. That is the vertical spacing. So if you multiply it, you get it TD value as 7.316. Or 7.32, whatever you call it. Then go to the third layer. This is your third layer. So third layer will be 1, 1.5 and 0.5. That means it will be at 2 meter. So third layer will be at 2 meter. Fourth layer will be at 2.5 meter. Fifth layer will be at 3 meter. Sixth layer will be 3.5. Seventh layer at 4. Eighth layer will be 4.5. Ninth layer will be at 5 meter. And 10th layer 5.5. So geograde will be placed at these depths. 11th layer will be provided at 6 meter. 12th 6.5. 13th at 7. Then 7.5. Then 8. 8.5, and the last layer will be at 9. So how many layers you are going to have? 14. This is the 15th layer, 16th. So total 17 layers of geogrid we required it. So total 17. This is the fourth layer. Similarly, fifth, sixth, seventh, and the vertical spacing is going to be 0.5 only. So friends, you are going to have the values. Those are going to be calculated depending upon the value of this. So 0.217, I think the calculation seems to be all correct. If there is any corrections, you can just check up with your calculator. I think whatever I am calculating seems to be okay. And so let us see that at let's say at 3 meter depth, we will calculate it. Here, what will be the value of TD? So at 3 meter depth or at 2 meter, let's go to 2 meter. So what will be the value of SV? 0.5. 0.5. The vertical spacing between two consecutive reinforcing layer, and the last one at 9 meter, the last one, that is the 17th layer, is going to be Z equal to 9 meter. So here the SV will be same, 0.5, no change. So let us calculate at 2 meter. So 4.774 into Z. So Z is 2 meter now. So we can keep it into 2 plus 7.471. So friends, we can substitute multiplied by SV, and SV is 0.5. So this is going to give you 8.50. Now it has increased to 8.5 TD value. So TD value is going to increase to 8.5 kilonewton per meter. Let us calculate at 5 meter. So Z equal to 5 meter. So at 5 meter, how much it will be? You can calculate at each and every layer. 4.774 multiplied by Z, and Z I am going to take it as 5 meter. and then 4.471 into SV is 0.5. So it is 15.67 at 5 meter. So it is increasing. 15.67 kilonewton per cubic meter. Let's make these columns little larger, otherwise it becomes clumsy, isn't it? So I will be making it little larger. I thought the space may not be adequate, but we have got, this is TD, a bigger core, a wider one. Then this is TA, the wider one, kilonewton per meter. And once you know the value of TA, then the calculations becomes quite simple. You can find out LE and then LE provided in meter, this will be kilonewton per meter, and calculate LR in meter, and then calculate the length in meter. So you will be able to get the total length in meter. So for internal checks, we require length and SV. So now this is the value, we got it at 5 meter depth, which is the 9th layer. Now let's see at 9 meter depth. So at 9 meter depth, the value of TD will be 4. At 9 meter. So into Z, that is 9. So from top to bottom we are going into 9 plus this into 0.5, and that gives you 25.218, that is 25.22. So this is going to be 25.22. This is the maximum. So friends, this is the maximum tension that is coming. In the last layer, at 9 meter, you are getting the maximum tension. So this is the last layer, 17th layer, and Z is 9. Here you are getting maximum value of TD. Now, how will you calculate the allowable tension? TA equal to TD multiplied by factor of safety, which is 1.5. All of you know it. I have already explained these things in my previous video. So very simple now. Simply you need to multiply. So 25.2185 multiplied by 1.5, if I keep it, this is going to give you 37.82. So this becomes 37.82. And here 9.81, 18. 9.18, or I will take it 1.5 multiplied by 9.18, that is 13.77, and this is 7 point. So next value we can also calculate 7.316. This gives you 10.97. So 10.97. This is 8.5. So we can see this. 8.5. This gives you 12.75. So it keeps on increasing, and here is the maximum value of allowable tension. Now what next? Next is you need to find out the value of LE. And LE I have already explained to you that can be found out from pull-out resistance. So how will you find out the pull-out resistance? So calculation of LE and LR is important. So next part will be, now this part is over. Next part is calculation of LR and LE. Now as I told you, with the vertical, this angle will be how much? This is 45 plus 5/2, and therefore with the vertical, this angle, the slip surface will make 45 minus phi r by 2. So if I take tan of this, so I can get at any depth h minus z. So I can find out LR equal to h minus z into tan 45 minus phi r by 2, where phi r is the angle of internal friction for the reinforced wall. So the first layer, this is the first layer. This is the value of LR on the left hand side of the slip surface. So how will you find it out? So find out this LR. So h minus z. What is z? Z is 1 meter. So h minus z, 9 minus 1, it becomes 8. So 8. So let us calculate tan 45. And what was the value of phi r? Phi r is 40. So 40 divided by 2, 20. So it becomes 25. So tan 25 into h minus z, that is 8, will give you the answer 3.73. So LR here is for first layer 3.73 meter, right? And next layer also you can find out, say 1.5 meters. So h minus z, z is 1.5. So 9 minus 1.5, it becomes 7.5. So next layer you can find out, that is 7.5. You require 3.49. Next layer at 2 meters. So 9 minus 2, 7. So if you go to 7, 3.26. Then if you go to 2.5, so 9 minus 2.5, it becomes 6.5. So 6.5 it is 3.03. So it's a decreasing. And the last layer, share. Let's say I'm going to calculate at 8.5 meter, that is the layer number 16. The Z will be 8.5. So 9 minus 8.5. This is going to be 0.5. So at 0.5, you require 0.233. That is very less requirement. 0.233 at the layer number here, at this layer, 0.233 meter, isn't it? Right? And calculate LE. How will you calculate the value of LE? From pull-out capacity. The pull-out resistance, you can calculate it very easily. So how will you calculate the pull-out resistance? The pull-out resistance we call it PR, which is equal to 2 times CI CR. So you know it. 2 times CI CR into LE. Last time we have given you the equation. That equation is valid over here. So you can just write it. LE into sigma V naught, the vertical pressure considering only overburden. If you take the surcharge, LE will be still lesser. So let us take only overburden. And multiplied by 10 delta. This PR must not exceed the value of TA. So this must be equal to TA. So the maximum LE is on the right hand side. So it is a function of TA, and TA is already known to us. What is the maximum value of TA? The maximum value of TA is 37.82. So this is maximum value 37.82. We can calculate LE at every length, and CI is given as 0.25. So 2 into 0.85. CR is 1 into LE, which we want to calculate, into what is sigma V naught, that you know it. How will you calculate the value of sigma V naught? That is the vertical pressure. Very simple. You all know it, how to calculate. It will be simply gamma R into Z. So the vertical pressure will be unit weight multiplied by Z into tan delta. The delta is found out from the pull-out test, and it is 30 degree. So in this problem, the value of delta is given to you as 38 degree. This is given. Must be equal to 37.82. Why I am taking the last one? Because here at 9 meter, the value of LE will be maximum. As you go up from bottom to top, LE is going to decrease. But we are going to provide the uniform length of the geogrid. We can calculate for all the depths from this expression. But for maximum TA, for maxima, you can calculate the value of LE. Therefore, the value of LE at 9 meter depth will be how much? So let's calculate. 37.82 divided by 2 into 0.85 multiplied by gamma R, that is 22, multiplied by Z, that is 9 meter, multiplied by tan 38. So tan 38 gives you the value is required value of LE is going to be quite less. So here the value is only, let us calculate here. What is the value? So LE for Z equal to 1 meter. So for 1 meter, LE at Z equal to 1 meter. What is the value? We can calculate it. So 37.82 divided by 2 into 0.85 into gamma r, and that is 22 into z. Z will be 1 meter into tan 38 equal to 1. 294. The value of tension is at 1 meter, it is 13.77. So there the correction. $13.77. Oh. This is 0.47. So this is 0.47. So all are less than, the LE here comes out to be 0. That means it is less than 1 meter, and minimum to be provided. This is the minimum value. Minimum 1 meter. So everywhere you provide minimum 1 meter. So this is approximately 4 plus 1, minimum 5 meter you have to provide. And if you provide little extra, let's provide it, the required is 5 meter. Let's say we are providing the total length as 7 meter. So throughout the length LE can be kept, summation of LR plus LE, that is approximately 5 meter, but what we are providing as 7 meter throughout. So the wall looks like this. This length is going to be 7 meter throughout. So what we have provided is more than the calculated value, and this is called the internal stability of the wall. So today we have checked for the internal stability, and in internal stability the pull-out resistance should be greater than or equal to the tension. So equating it to the tension at different depth, we are able to calculate the value of LE, and LE plus LR. If you sum up, you get the value of L calculated, and this is L provided. So the L provided is 7, 7, 7, 7 throughout. So I am going to provide 7 meter. So in the next, I will be checking for external stability in the next video. So I have got a reinforced wall whose vertical spacing is going to be 0.5 meter between layer 1 and layer 2, and it has been the first layer at this. So you can, PHR is already known to you in terms of this. This is equal to this. So you can very well calculate TD, you can calculate TA, you can also calculate T ultimate. In the last videos, I have told you how to calculate T ultimate. Let us see how to calculate T ultimate. The ultimate tensile strength of the reinforcing layer will be T allowable, which you have calculated, multiplied by reduction factor for installation damage, which is 1.5, multiplied by a reduction factor for creep, which is 1.5, multiplied by chemical and biological degradation reduction factor for degradation, that is 1.5. So T ultimate, the ultimate tensile strength, what is the maximum value is 37.82 kilonewton per meter multiplied by 1.5 cube. So 1.5 cube multiplied by maximum tension, that is 37.82 equal to 127.64. So this is 1.5 cube gives you the ultimate tensile strength equal to 127.64 kilonewton per meter. So you can procure the geograde having tensile strength, ultimate tensile strength more than 128 kilonewton per cubic meter, so that the allowable tension is going to be as per this maxima, and throughout you can use the same geosynthetic reinforcement. So this is how you can calculate LE, you can calculate LR, you can calculate the total length calculated and provided, and you can construct your wall. Different approaches I will tell you in my next video after checking for external stability. Thank you very much.